You think? Three, seven. Over next week. I was like, I would have this. Yeah, it says you're gonna come to. Thanks. See who goes like these. Pretty sure. Not about it. And it's one of it. Yes, I don't know if that's on. I haven't done the cross. It's not so bad though. Check the schedule, see if we're working. Only here, right? Yes. Six. 6 years. Yeah, that's because we have the weekend. 6 years left. Oh. Once. Yeah, they resold about 6 years. They got some. Jason. I don't think that has this one.
Good morning. Do you have any questions? Any more questions? Are we doing okay so far? So maybe we could take the steps early. So we're gonna finish all 6 sessions on chapter 1, and then 1 week after every single exam, we're gonna schedule tests for chapter 10. The original plan, I actually labeled it September because it was giving us time, so then we can have the homework all finished. I did see at least 1/3 of the class has finished most of the assignment. The original dates. So original date was September 4th. That's after this week. So hopefully this week we'll finish everything in chapter 10. And then if you still need a little bit more time on section 5 or section 4, we should take that 1 week. Next Tuesday was the planned time for the test. Any question? You feel like that should be okay?
Should I open the schedule list?
So chapter 10 supposedly was more a foundation, a basic section, and it's the bridging section, bridging chapter between Calc 2 and Calc 1. Many of you might have reviewed or worked on some of the chapter 10 questions by the end of Calc 2. But now we did try to learn it from like treating it like a new chapter. So if you have been up to date with your homework, you probably have done the majority of the work. There's only 2 sections left for this week. So hopefully this week we'll finish section 5 and 6. We should be ready for the text next week. Any question? I try to schedule like at least 1 week before the test days. We have enough time to be prepared or change the schedule. If you want to, if you have anything happen the day, like September 4th, you have something that you have to do and reschedule, or we can take it early so we can make a plan ahead of time. Right. Now I was working on some of the questions here just to review what we're doing. Section 5. So 10.5 is the equation of lines. So normally with equation of line, there are 2 key information that we need to know. For determining a line, we need at least 1 point, which like fix the location of it. So if you have a line, if you have a point already, and then to draw a line, you can go this way, this way, this way, or this way. So there's many different directions that you can go from that point. So to determine the line, number 1, you have to fix the location by a single point, and then you now have to determine where do you go from that point. So we need a point and a direction. Now to determine a direction, we can't do it with only one number. So if you have a 2-dimensional space, then you need a 2-dimensional vector for the direction. If you have a 3-dimensional, like in space, 3-dimensional space, then you need a 3-dimensional vector to be able to represent that vector. And we did talk about equation of a line last Thursday. To determine equation of line, you can identify the point, which will be a 3-dimensional coordinate. So the coordinate for the point and the vector, the 3-dimensional vector. So we can write a point plus t times the direction vector. We can write a vector form of the equation of line. Now, the vector form of the equation of line, you can identify every component of that vector. So you can write x equal to the first component, y equal to the second component, z equal to the third component, which will be the component form of the equation of line. Then every form of these vector form or component form, you all have t carried in your representation of line, because t is like along the line which point we say that t is the relative location, like relative to the original point. Where do we stay on that line? The t is what people call the parameter. So sometimes people do not like the line equation of lines having an extra variable t in there. So we can remove the t. We can figure out a way to get rid of the t in our equation, and turns out that equation will be called symmetric equation. Okay, so 3 forms of equation of line. The first 2 are the most common. What you see on the screen is equation of line that you see in question number 4. If you are on your computer or with your device, you may be able to find your question 4 and compare this one with it. This one is if you already have this is the parametric form of the equation. Now, given that equation, how do we identify the point P and the vector V? So vector is to determine the direction, the point is to determine the location. In this case, the one that stands by itself is the component of the point. So the point goes, if I do vector form, let's just do this way. Like, do I do it this way? Do I do it this way? I hesitated. Let's try it in the vector. -5 and then -1 for the second component. I'm identifying the number. Third component is -1. Right? This first one's supposed to be the vector that determines the direction. So you can look at the one I multiply by t times the direction vector. So that all those number multiplying t are component for the vector. So that would be -2, -5, and then 5. So this is how we would answer even the point. So obviously I should switch that to a representation point. Let me change it to one. So this is solution for number 4. Just try to review the vector form or parametric form of equation of line. Try to go through the rest of the first few. They're short. Spend a lot of time on that. Number 5 is, say if you have a point and then you have this vector, how do we write equation of line? It says to find the vector equation of the line, which involving the parameter t. So we write mx plus b, or the point stand by itself. So you would have, now we have to turn it into a vector. We write vector form of the line. And there's 0, there's -4. So that's the location plus t times the direction vector. Here is, says parallel to this vector, so obviously that's our direction. So 2, -4, and 4. I just try to illustrate how to answer number 5. And then again, with all these thinking in this exercise, we grab on or hold on to these two key information, the point and the direction vector. This one parallel to that line, which means all we care is the direction. And this is writing a parametric equation of the line, meaning that we're gonna have the x component, y component separate. The x component is gonna be 5, and then there's a plus 3t. So we're writing a equation of a line that's parametric, the parallel to the given line. This given line is already in a parametric form, the x form, the x, y, and z. So all we have to do is keep the direction, which is 3, 5, -1. We keep the direction vector, but change the point. So instead of 1, 5, 1, we switch it to 5, 0, -1. The second component is still gonna be 0 plus 5t, so 5t. The last component, we need the -1, but we're gonna minus t in the direction. So -1 in the b component. That's how you construct this equation of line. So if we understand the logic behind it, know that which part you change, which part we don't change. So the 3t, 5t, and -t, they don't change. We only change the form, changing the initial point to the given point. That's how we determine the equation of line when the point and the direction is hidden. Any question? Okay. Are we okay? So know that when you know the direction and the point, then the equation of line can be determined pretty quickly. So these are the few questions that they don't take a lot of time if we understand the logic behind how we solve these questions. Now, this is the one that we solved, I think. We're trying to finish up 1.5, and we have already introduced the equation of the line in 3 different form, and we went over Thursday, last Thursday. So equation of line, we need a point and the direction. So the bottom formula will be how we construct the equation of line. And we can compare that with the equation of line that we had in Calc 1, now that we have the equation of line in 3 dimensions. So the format of it is not too far apart, except those vector notation indicate a more complex structure of how we represent point, how we represent the direction. So in the 2-dimensional case, the direction is a single number m, but now in the 3-dimensional case, it's actually a vector d. Now, moving forward, we summarize with equation line into three different forms: the vector equation, the parametric equation. These two are similar, vector form and parametric form. Fundamentally, they're pretty much the same, which both of them involve the parameter t. Number three is when parameter t is simplified out of the whole formula. That's when we have symmetric equation. You see that we have x minus the point, y minus the y value, z minus z value in the numerator. In the denominator are the component for the direction vector. So we can see some pattern when we need to construct our equation. Hopefully this pattern give us some indication of how we're gonna construct it. All right, and then there are a couple of examples. This one is saying, now if we have a direction vector, we have a point, and we construct the equation which is building them together. Put down the point, put down the direction vector, having the direction vector multiplied by t. So that's the vector form. Now identify x, identify y, identify z. Now we have a parametric form. Now with all three equations, simplify the t out of the whole formula, we have our symmetric form. Any question? Just try to review. Maybe it's kind of an extra thing. All right, then we were talking about relation. This is when we stopped. So relation between two lines. I guess we should work on the quicker question before we move on to a very different topic. So this is today's quicker question. Suppose you have 2 points. How do we determine equation of line that is determined by these 2 points? So the idea is any equation of line involving points, which we have plenty, we have 2 points. You can use any of these 2 points. You can use 2, 2, 1, -1, or you can use 0, 3, 1. So it looks like A or C has 2, 1, -1 as a point. These vectors are being given in vertical form. Remember, vertical form or horizontal form. They're essentially the same thing. It's just a way of representation. The direction vector is different. You have to calculate it. Remember, how do we calculate direction vector? If you have a 2 point on the line, connecting those 2 points, that's your direction vector. So for example, the one you have on the board, you have P and Q. So let's say we use vector PQ as a direction vector. So D equal to PQ. All right, you want to write on your calculate yourself. You have the coordinate for Q minus coordinate for P, 0 minus 2, that's -2. And then for the Q, second component is 3. For P, the second is 1, so 3 minus 1, 3 minus 1 is 2. The last component is 1 minus -1, which is 1 plus 1. That last component is also 2. So that's our direction vector. And then therefore equation of line will be same. That's when you use the first point. That is 2, 1, -1. With a plus t times the second times the direction vector, which goes -2 and 2 and 2. So that's the equation of the line right there. So I hope that you start writing it out and then see which is the appropriate equation for the line. And that's pretty much an exercise reviewing how do we construct the equation of line when the points, when plenty of point is given, and we probably could push them up with the points. So this is a typical example when the equation of line are being determined by given 2 points. Everyone's answer. If you need more time, raise your hand so we can see. How many? So I think I have everybody, right? Answer C. Anyone need more time? Okay. So that's for attendance. Continue. Where we left, we were talking about relation between 2 lines. Now that the equation of line is there, we have 3 different forms. But what if we got 2 different lines? Now we mentioned that the relation between 2 lines are form relation. two line, these two line might be just so happen they're the same line, first scenario. Second one, what if they're parallel? Same line or parallel, they would have the same direction. So D1 is parallel to D2. When they are all the same line or when they're parallel, they would definitely have the same direction vector. The other two scenarios, what if they are not having the same direction vector? If they don't have the same direction vector, there are two possibilities. Either they intersect, so they will have a single point. When two lines are intersecting, there's only one point of intersection. There's one intersection point, so they share only one point. Or these two lines, they're not going in the same direction, yet they're not intersecting. It's possible. So pretty much they're living in two different planes, and these planes are parallel, but generally these two lines are what we call skew lines. So skew lines is lines are not following the same direction, and yet they're not intersecting. So in that case, we will have to determine which situation it is. Are they intersecting or are they skewed? What we can do is try to find the intersection point, assuming that they don't have the same direction. Try to find the intersection point. If we cannot find any intersection point at all, if there's no solution, then they will be skew lines. If we're able to find the intersection point, then obviously they're intersecting. So that's the procedure that we did for this example. These are two lines, line 1 and line 2. Line 1 has the vector 3, -1, 1. Line 2, the direction vector is 4, 1, 2. So 3, 1, 3, -1, 1, and 4, 1, 2. They're definitely not parallel. Parallel vector, we can tell because their component will be proportional, will be within the same proportion. But right now they're not in the same proportion. You can see the proportion, they go 3 to 4, 1 to 1, and then 1 to 2. So definitely not the same direction. They're not going in the same direction, so they're not parallel, they're not the same line. That leaves us only two options. They're either intersecting or skew. To determine whether they're intersecting or skew is set it up in a way that we try to find the intersection. So what do we do to get ready for that? We make sure that we're using two different letters. The first line, we're using T as the parameter letter, the parameter variable. The second line, we use S for the parameter variable. That way, we know typically, even if two lines are the same line, they could be using two different parameters, so they could still be working fine. So we absolutely are not supposed to use the same parameter if there are two different lines. So then we can set them equal. We set x equal to x. 1 plus 3t equal to -2 plus 4s, and then 2 minus c equals 3 plus s. So x equal to x, y equal to y, z equal to z in the setting in order to find intersection. So whenever we, in math, finding intersection point has to be a consistent topic. So a lot of time you have this graph, this function, this function. Let's find their intersection, graph them on the same xy plane, and then you're like, where is the intersection? The way to solve it is you pair these two equations. You want to find a common solution. So what we are doing here, the x equal to x, they have to share the same x and y. If it's two-dimensional, if it's three-dimensional, they have to share same x, same y, and same z. That's the property of the common point, intersection point. So what will happen over here at the lower half of this page, we set the x value equal, y value equal, and z value equal, which end up having two variable equation, but we got three of them. And when you have two variable, you only need two equations to solve it because your solution matrix will be 2 by 2. But now you have one equation that's extra. So that one equation is either consistent with what you have, which means they share the same solution. All three equations share the same t, same s. However, if you got two equations and solve the solution for t and s, and then you plug into the third equation, it does not work, which means the three equations are conflicting. That means the three equations as a system does not have a solution, which will be this case. We take the second, I think the second and last one has smaller coefficient. And then also because this equation, the third one has t equal to, so that t can be substituted into the second equation and solve for s. So second and third combined is easier to solve. So combine them, you'll be able to solve the t and s. which end up being, 1 and -2. So t equal to 1, s equal to -2, and we plug into the third equation, which is the top one. And it doesn't work. So, which means that there's no intersection. The whole system equation have no solution. We set the equation up to solve for intersection. If there's no solution, then there's no intersection. When there's no intersection, there's still lines. So that's the logic behind the entire solution. The solution is already being presented here, but we want to be able to understand it in our own way. So hopefully that's my own way of thinking about it, how I draw my conclusion. But you can definitely look through it and see if you can understand. When you work on those homework questions, these have to make sense for you to do your own, make your own calculations. Any question? There are at least 2 homework, or maybe 3, about relation between lines. And then this will be one of the examples. And then let's look at one more example on the relation between 2 lines. We have line 1, line 2, kind of pair them together. Maybe it will be a typical presentation when you do your own work. You put on line 1 on this side, line 2 on the other side, and then maybe later compare their vector and then compare their points. So we first will look at their direction to see if they're parallels. You see the direction? 1.6, 2.72, 6.36. And there's 2.9, 4.93, and 6.09. One thing we can see is the sign. On this side is positive, positive, negative. On that side is negative, negative, positive. So line 1 on line 2, as far as the directions tend to pair in a opposite way. And then we're going to look at the value. I want to see if the vector are parallel. And instead of calculating unit vector, remember how do you turn the unit? You find the magnitude and then every component divided by the magnitude to find the unit vector. And then you compare their unit vector to determine if they're parallel. I like to look at their ratio. So the ratio between their x component is 1.6 to 2.9. Between their y component is 2.72 to 4.93. And the last one is 3.36 to 6.09. So if all 3 ratio equal to the same thing, then the first vector, the first line is parallel to the second line. So that is a quick way. All you have to do is right now your calculator and do 1, 2, 3. If they are identical, then they're parallel. Or they're in the same direction. Parallel now we have to say their intersection point. Are these the same? Have you tried? Is all 3 of them same? 1.2 divided by 2.9, 2.72 divided by 4.93, and 3.36 divided by 6.1. Are they the same? They're the same, right? They're the same. So obviously they do have the parallel direction. You can write like D1 is parallel to D2. They're parallel. Their direction vector are parallel. So that is only 2 possibilities. Number 1, these 2 lines are the same line. If they're the same line, their direction would be in the same direction. The direction vector will be the same direction or parallel direction. Number 2, they're parallel. That is, they are going in the same direction, but they don't have any point in common. So these are the situation, right? Right? So then we have to answer the question. Do they have any point in common? So whether they have a common point we answer same line or parallel. If they have some point, any point in common, then they will be the same line. And then if they have any point in common, they will be the same line. But if they have nothing in common, then they will be parallel. This is different than when they're going into opposite direction. We don't have to solve for that intersection. I mean, but you may think about, do we have the x equal to x or y equal to y, z equal to z, and so there's a lot of decimal in that system. I do not want to set this x equal to that x, this y equal to that y with so many decimals. I can imagine the level difficulty maybe a lot, but maybe not. Maybe If they're proportional, it's not too hard to tell. But we can do this. If the direction vector are parallel, then there are two things. Is either these two lines are the same line or they're parallel. Now, how do we tell if they are the same line? Then any point on the first line would also be the point on the second line. So you can test point instead of. So this is not in the intersection point because there only have one intersection. Serving for that one intersection was hard, but it's something we have to do if they are not in the same direction. But now that they're parallel, they don't share one point. If they're the same line, they share a lot of common points, right? So we don't have to search for point. Any point can be a point for testing. So what we do, we will grab any point that's easier. I'll prefer the one decimal point. Let me start writing it since I'm recording this. So to think about it, let me make sure I did. Oh, there's a lot of you online. Maybe then I might have to send a link. Sorry. Yeah, I didn't notice more student attending online. That means I should write more on the board, right on the computer. So let me give you your link. Okay, I see Jada. And Bella. Andrea. You guys bookmark this link. So next time if you're attending online, you'll be using the same link to answer the bigger question, so I don't have to send it again. Let's go back to that question so you can actually answer. You already know the answer C. So let me turn on the scanner. Are you able to open your link and click on C on that page? It's a single web page for your clicker question. Are you able to answer? Any question? I see Jada already clicked on the link. Once the link is open, you should. Okay, the link is reported. Everybody answer the C. All right, back to the question that we're working on over here. We already know that the this two line have the same. There's a vector. The direction vector is parallel. And then, so the only question we have to answer is whether they are the same line. So right now, what we observe is that B1, which is this vector, right? And this is the second vector, that's the D2. So what we can tell is B1 is parallel to B2. Okay, so then for these two lines, the only question we wish to answer is, are these the same line? Okay, if these two are L1 and L2, if they're the same line, they will share all the point. They will share all the point. If they're not the same line, they will be parallel. Right? So all we have to do is, you see the first line had this point. See from the equation, they got -0.7 and then 4.2 and then 2.3. So that's a point. This one of the point on the first line. So it is on line 1. So all we have to do is answer the question: is it also on line 2? That's what we need to make sure. If that point, which is on line 1, we already knew it because it's in the formula. If it's also on line 2, then they share a point, right? So if they're going in the same direction and they share a single point, and they're going in the same direction, they share every single point, right? So parallel lines, if they share one point, they share all the points. So all we have to do is make sure we set an equal and see if it's fitting the second equation. So say we're setting the x equal to -0.7 7. So, and then we find out the S that could fit this scenario. So to answer the question, if it's on line 2, we're gonna find the proper S. So then you move the 2.9 over the 2.8 plus 0.7 is 3.5, which equal to, we move the 2.9 S to the right side equation of solving equation. 2.8 minus 2.9 S equal to negative 0.7. So this is an equation I'm trying to solve. And solve this S for, solve this equation for S. Then the other side equation will be 2.9. Yeah, doesn't look very nice. So I have the value for S equal to 35 over 29. Right, and then we're going to plug into the second equation to see if you're able to get the 2. Right, the second equation is right there. So we're going to calculate if S equals this number. So what happened to the Y value? Y will be, we already have a value for S, Y will be 10.15. This is not short, but it's definitely shorter than if you were setting up to solve for intersection. The S is multiplied by 35 divided by 29. I just want to double check to see if it's a 4.2. That way we can see the intersection. Grab the calculator. It is 4.2. So, okay. And then we can also double check the Z value to say, giving this S value and the number for S is the Z equal to the same thing. So Z will be negative 5.05 plus 6.09 multiplied by 35.9. And we're going to save the number equal to 2.3. We're going to need a calculator. So copy and pasting. It is 2.3. So according to the formula that's in the L2, and turns out when you are giving the S equal to, if S equal to 35 over 29, then the L2 produce the number negative 0.7, 4.2, and then D equal to 2.3. So the point that was on the first line, it is also on the second line. So the conclusion would be, yes, they are the same line. Even though they look drastically different from each other, turned out they're actually the same line. Any questions? Are you okay? So it's kind of tricky. Sometimes situation just turns out to be, sometimes they're parallel, sometimes they end up being identically the same line. Okay, so let's go back to this example. That's how I would treat this question. I would look at the direction and look at any common point between the lines. The text solution is this. So instead of dividing 1.6 divided by 2.9 and 2.72 divided by 4.96, I would look at the ratio between X and Y and Z. The textbook solution is taking every component divided by the magnitude of the vector. You know, the magnitude is root of X squared plus Y squared plus Z squared. That's the magnitude. So you're going to see a lot of decimal in the unit vector, and then you're going to find the unit vector for D2, which is the vector itself divided by the magnitude. That means every component divided by the magnitude of the vector. And you can see their opposite component, the opposite unit vector. This is verifying this two vector is parallel. So now once they are parallel, then we're going to look at point from the first line. That point is on line 1. So we want to see if it's a lot on line 2. So how do we determine if it's on line 2? The textbook maybe have a better solution. What I did was solving a plugin and solving for S and plugin. The textbook is figure out a symmetric equation of the line, which is like X minus X divided by the X component of the direction vector, Y minus Y, that's the Y. And then that's Z minus Z. So this is try to tell if a point is on the line using the symmetric equation. That was in the same example earlier. So whether all three are equal to each other, that's how we can tell if they're on the same line. this method of determining whether a point is on the line is more symmetrical because you have symmetry between x, y, and z. My method is not very symmetric because I did x components for solving for s and treated z and y. So for y and z is symmetrical, but for x is not. So I think both way are logically correct, depending on how you, which one do you prefer. Any questions? As you can see, I provide a different solution than what's in the textbook. I think both are valid logic, valid reasoning, depending on which method. They provide the same answer. So the answer will be the two line are the lines. Any question? Right, so these are ended our topic on discussion. If you have two lines in space, what kind of relation do they have? Depending on the setup of the equation of line, they could be the same line or parallel line, intersecting line or skewed. So these are four options, and then the way we can determine them is first look at the direction vector. Based on the direction vector relation, then you separate to two groups. If they're parallel, then they are either the same line or parallel lines. I mean, if the direction vector is parallel. Second, if the direction vector is not parallel, then they're either intersecting or skewed. And then from there, we go forward at the points on the line. All right, let's move on to other topic in the section. Now that we have relation, now we have to answer two questions. Number one, if two lines are parallel, how far are they apart? So we try to answer that question. The answer to the question will be, if the two lines are parallel, then it's very easy to find the distance. You pick any point on one line, try to find how far that line to the second line. That is the distance between that distance will be. So if this is a vector, this will be the magnitude vector. So the distance to determine the direction between two parallel lines, any point on that first line is distant to the second line. The distance from a point to a line would allow you to calculate distance between two parallel lines. We also need to determine if two lines are skew lines, how do they determine the direction between the two? So the method is different. In that case, if they are skew lines, the thing that you have is every line has a point in its formula equation, and every line will have a direction vector. And they're actually going into two different directions. So both of them has to be in your consideration. But if they're parallel, then they're in the same direction. So if they're parallel, then they're only one direction vector you should consider because they're basically going to the same direction. And then all you have to do is pick out one point and try to find it. So here we have, we want to calculate what is the distance from a point to a line. Now here is a line, and then every line have a direction vector and also have a point. So we have the point P that you see in this picture. We also have direction vector D. Now, a random point over Q, and you can imagine Q will be the position vector in the second line in a parallel line. Again, since they're going in the same direction, we don't have to worry about direction. You can consider this is a procedure for a formula to determine the distance from a point to the line or determine the distance from a parallel line between two parallel lines. So both of them will be following the same procedures and calculation anyway. So let me try to use my own logic. You can see the solution is already on the board. If you can look at the first one, look at the second one. If you feel like you already understand, then your mathematical thinking is good. But let me try to explain from my perspective. It's pretty much trigonometry, or right triangle trigonometry that we're doing here. So say here you got a point, right? So how far from that point to this line? This distance is what we are drawing, h, right there. So how do we find out measurement of h? It's really a distance, therefore it's a magnitude. So to calculate h, see h fitting in this right triangle here, right? And then this is a point, and that is a point. With point, you can determine a vector. So we have a vector in Q. That's already in the picture. But then this is a distance calculation. In the distance calculation, the learning concern is how long they are. So this length is a hypotenuse of the triangle. The length of this one is magnitude of PQ. Now down here is a direction vector. So then of course this vector and this vector will have an angle theta between them. And then the angle theta is theta between these two vectors. Now H is the opposite side of theta. So H is a height, it's the distance would equal to, you see sine theta would involve H. So the right triangle symmetry tells us sine theta is equal to opposite over hypotenuse. The opposite is H. The hypotenuse in this triangle that we're talking about, right triangle symmetry, opposite over hypotenuse. The hypotenuse is the magnitude of vector PQ. All right, so this is really a right triangle symmetry about sine theta. So multiply both sides of the equation with the denominator. Now we have H is equal to magnitude of P vector PQ multiplied by sine theta. So this is really our calculation idea for H. H is the distance between the point and the line. So we need to figure out a way to calculate it. Now, so far, the problem is we know point P or point Q if we have equation line and coordinate of the Q. So PQ is the problem. Problem would be sine theta. Which formula involves sine theta? In last section, cross section, we have sine theta. So according to the cross product, we go PQ cross vector D, and the angle is between vector D and vector PQ. This magnitude of the cross product equal to cross product itself is a vector. The magnitude of cross product is a number. This number equal to magnitude of PQ. This is the formula in 10.4. If you forget it, you might want to double check. Multiply by the vector D, and then multiply by sine theta. This is the one single formula that contains sine theta. So the reason that we write this formula down is because we wish to have a formula for sine theta. So according to what we have here, then sine theta, you divide out that same. Both sides of the equation divided by the multiplication of the magnitude, we'll have sine theta. Sine theta actually equal to magnitude of PQ multiply PQ cross vector PQ cross vector D, the magnitude of this. Remember, this magnitude is really the parallelogram's area. This is the parallelogram. Using this side and this side, that's the area of the parallelogram, right? Divided by magnitude of PQ times magnitude of D. So that's how you can calculate sine theta. And not a lot of places we need sine theta. When we try to find angle, we prefer cosine theta and dot product. But here is one with sine theta is easily accessible. So now we're going to finish our original calculation for H. H is equal to magnitude of PQ vector magnitude multiplied by sine theta, and yet sine theta is equal to this. So we multiply that into the place where you need sine theta. So originally you need a sine theta here, but now we put it there. Now we can cancel common factor. This denominator cancel this numerator. So we end up having a little formula that goes magnitude of PQ cross D. This magnitude actually is the area of the parallelogram. So divided by magnitude of B, okay, which would end up be giving you the height of the parallelogram. Remember, this is a parallelogram using B and PQ as a side. Then this is the area that we're calculating. Now, the area of a parallelogram is the height of the parallelogram multiplied by the base. If you divide the area by the base, you get height, which is theoretically reason. So this is H. Okay. So if you multiply the height with the base, is area of the parallelogram. So in reverse, area divided by the base, which give you the height. And that's another interpretation of it, so that we will have a way to remember how to calculate the height. So here is my interpretation for the formula. And that is giving us a way to calculate that you have to treat it this as the formula. So height distance between the point to a line is equal to the magnitude of the cross product, that is the point in both lines cross the direction vector, since they share the same direction, and that is the magnitude of the cross product divided by the magnitude of B. Okay? Which in turn, you see PQ is this one, H is here. So we are making a perpendicular adjustment to PQ. So that's kind of another interpretation. You got D here and D here. In a sense, we're trying to cancel out the D to get PQ correctly. So PQ is this way, make it perpendicular. So anyway, that is a formula. So let's try to look at this example where we are applying this formula. Okay, one of the homework question is calculating distance from a point to a line. So let's grab that question. All right, that's question 9 on the homework. So we find some examples, and hopefully we kind of, with enough practice, we understand the logic behind it. Because whenever we see a new formula, and if our cross product is new in the first place, now we have this formula. Okay, so see how we do it. So here we have points and the lines. Okay, so the point is, so there's a line, the line has point, and then here we got a point. So we got a point that we say P is -4, and then 4, and then 1. So this is the one being called P. We also have another point, the point that's inside the equation of line. Let's call that Q. Q is equal to, we have a point to 1, and then there's -5, and there's 0. Are we okay of determining the point from the equation of the line? Any questions so far? All right, once we find the point, I mean, we're trying to follow the formula. So I'm trying to name the P, Q, and then D. The vector D is a vector, direction vector. We have negative T in the first component. That's -1 as far as the slope of the X component. And then Y equal to -5, slope equal to 0. I mean, we have a T in there. Z equal to 0, so slope equal to 0. There. So that's our direction vector. Are we okay so far? So now we need to do a cross product, and it has to be here. It's PQ cross D. So we have P, we have Q, but we have to create a vector PQ. So PQ is equal to, I'm making it into a vector. Q minus P, so that 1 minus -4, that was 5. -5 minus 4, that's -9. And then 0 minus 1 is -1. Right, so that's PQ. We already have the D right in here. We need to do a cross product, so try to one below the other one. But the nice part of it is there's a lot of 0. To make the cross product easy to follow, I'm adding one more component, create that vector column. Okay, so now let's write down the calculation for PQ cross vector D. So what is it? Cross multiply and subtract. 9 times 0, 1 times 0. They're all 0, so the first component is 0. And then here we're gonna this multiply and this divide, and then -1 times -1 is actually positive 1. Hope that you follow me. And the last component is these two, we cross multiply and get back into the second component, so we use first column. 5 times 0 is 0, and 1 times 9 is 9, -9. right there. The formula is actually here's right. I sell since my writing and to get messy. So that's our calculation for the distance between the two. So this is equal to. The rest is all magnitude calculation of the magnitude of vector, right? Are we okay so far? So the PQ cross D is done. These are all vector. I was typing is a kind of difficult to put an arrow on top of it. So the cross product is already there. All we have to calculate magnitude. So it's square root of 0 plus 1, so it's 1 plus 9 squared is 81. Square every component, add it all together. I didn't add 0 because it's 0. And then the denominator is this one, magnitude of this one equal to 1 because it's square root, 1 squared plus 0. So 0. The whole thing have a distance of root of 82. At least on my version of it, you have different number. Are you with your computer? This is a question 9 on 10.5. Anybody already did this question? Any concerns? All right, so we're gonna go back and answer the question. The answer should be the how far apart is square root of 82. That's why it's. So that's how we answer this. Any question? All right, we're gonna work out. Well, let's see if there's another one. So work out one more example. We'll see. I'll ask you the question. So here we have a distance d of a point P to the line. So AP is the length of the component AP. That is all orthogonal to AB. So essentially, we're doing a projection onto the perpendicular direction instead of the horizontal direction to the vector AB. Now, but we're gonna follow our formula. So here you have point P, and then this is to vector AP. So how are we gonna do it? We have to create our own direction vector. Let's copy that question. It's question 10, which applies very similar thing. All right, so let's see. Okay. So we're gonna follow very similar reasoning. Here we have P, and here we have AB. What we're gonna do is AB is along the line, right? So your this direction vector, because the point A and B is forming the line is through this two points. So your direction vector is going to be the vector AB. It's your direction vector. So the direction vector is going to be 1 minus -4, that's 5. And then 5 minus -1, that's 7. And then 4 minus 3, that's 1. So that's the direction vector. So now that's our direction vector. And then here is the AP vector. We don't have PQ, so here I'm trying to convert. So we're going to have AP vector. So we're trying to get a like this is all orthogonal to this, like perpendicular to this. But we don't have that vector. We have this vector. That's what we're going to cross that for. So we have AP. And now we can calculate it. AP is going to be that's P. This is A. So P minus A, that's 8, and then 2 minus 1, that's 3, and then 4 minus -4 minus it is -7. Okay, so we are going to cross, I mean, this one and that one. This is the AB on this side, this is the AB on this side. They will form a parallelogram like this. Okay. Area of this parallelogram will be magnitude of AP cross D. D is the direction of the line, right? And divided by the D. Direction vector of the line will always be in the numerator and in the denominator. This is our calculation for H. Just try to match it. Like, are we okay? Yes.
Yeah, in the vector AB shouldn't be 5, 6, 1.
The calculator wrong. Oh, it's 6. Thank you. Thank you. I made a mistake with the mental math with calculation. It should be this 5 minus -1. It should be 6. Thank you. All right, yeah, so, I should pair them the other way around, but we're finding the magnitude anyway, so AP cross D or D cross AP won't change anything, since we eventually are gonna take the magnitude, which will make them all positive anyway. So I'll just do the cross product like this one cross this one, instead of this one. So we're gonna do a cross product. Try to make it virtually look like a two-vector matrix. And then we're gonna add one more. There's 5, there's 8, so you can calculate the cross product easily. So now I'm sure the D is already there, so the magnitude will be root of 25 plus 36 plus 1. The denominator is the magnitude of the direction vector. Numerator is the cross product of these two. So let's see. The first component is going to be the third component construction. So it's negative 42 minus 3, that's negative 45. It's weird to find it writing short, I might skip something. Right, so here is cross multiply and subtract, so that's 8 minus negative 35, that's 43. And the third component is these two, 15 minus 48. Getting slowly less confident about my calculation. 15 minus 48 is negative 33. So that's the cross product, and then we need to find the magnitude of the cross product, which will be the numerator will be 45 squared plus 43 squared plus 33 squared divided by the magnitude of the denominator, which is 62. Okay, the numerator definitely need a calculator, so let's go back there and then put it in there. Numerator is square root, big square root calculation, denominator is square root of 62. I did it mentally, let's hope there's no error. So this is a 43 squared plus 33 squared, then plus 45 squared. I wonder if I got it. 45, 43, and 33. 45, 43, and 33. That's it's mixing the pieces. So that's the entire calculation. I'm trying to fit everything in one page, so it's a little bit shorter on some of the steps. The cross product, I did it in one step. Any question? Thank you for helping me fix that error. Let's try a practice question on your own. I hope that you kind of get the idea. Just cross product and then find the magnitude in the numerator and then the direction vector's magnitude. So here you grab a question for us to practice. So and then here is question from the distance calculation. Okay, so this one we have a clear indication of the point, which is normally called Q, and then the point -1, 1 is the point P. So we have these 2 points. You have to find the vector PQ. That's P, that's Q, and here is the direction vector D. So let's follow the formula that we did and see if you're able to find distance calculation. Data distance calculation. I follow. I either feel like if there's anything more complicated in these 2 sections, it will be all these distance calculations. Right, so you basically got Q that is So we got Q, which goes 2, 5, 6, right? And then we have point P that's -1, 1, and 1, right? And then we have the direction vector that is say 1, 0, and to finish the distance calculation, you have to turn those 2 points into directions. So the vector PQ is equal Q minus P. We are it. It was 3 and 4 and then 5. Q. And then we would need to find out PQ cross D. So you put one factor below the other factor to make it easy for the cross product calculation. I added 3 and 1 there just so we can get cross product. So PQ cross D is equal to, so that's the numerator. Numerator has to be the magnitude of the cross product. So we are calculating cross product first. We would have double check your calculation. To watch out for myself, whenever I try to do it faster. Okay, occasionally have calculation error. Had it backwards. The first component is 4. Second component is the 2. That's the crosswalk, right? Sorry. Right? Okay, so then we can start calculating the distance. According to our formula right here, we follow all this notation, so it's easy to apply the formula. That's why I try to do the PQD, because in our formula we have PQD, so we try not to confuse ourselves by using new notations. So here we are. So the calculation numerator is supposed to be magnitude of the cross product. We already have the cross product, we didn't do the magnitude, so here we are. Inside the root is 16 plus 4 plus 16. See, it's perfect square.
Yeah, that'd be 6.
No, thank you. So numerator is actually 6. Now move on to the denominator. It's square root of the direction vector. This is direction. This is direction. Making it easy to view that one. All right, so it's actually 1 plus 1 after we squared. So it's over 2. So that's our final answer. You're gonna rationalize that number to a number that we can match with our process. That's this exercise, and the main purpose is to be able to get really familiar with this. So next time we see that question, we're gonna see how we can. Yes.
So 6 over 2.
The answer, right? So it should be, we multiply the denominator. We rationalize, we multiply by 2. You measure the denominator, 6, 2, and then the denominator, which is 2. And then you can simplify 6 over 2 into
I see.
so that we can find the connection. Okay, let's go back to that page so we can see how our pencil is being recorded. Should be everyone. Okay. Raise your hand if you need more time. Actually, now we're gonna move on to another topic. I have another business calculation, even though we're nearing the end of the class session. That is, what if we get 2 lines and we want to find the distance between these 2 lines? So how do we do it? So basically we're trying to find some way to manage to get a little bit closer to the distance. These two lines, they both have a point, so we can get this 2 point and this point connect to the other point, which will be a vector. So you can get point P1, P2. From P1 to P2, you can get a vector. And what we're gonna do is we turn that vector to the perpendicular direction. So we're gonna try to project the vector onto the right direction. How do we get the right direction? That is the D1 and D2 are in a direction, like this one's going this direction, this one's going this direction. We need to find something that perpendicular to both. And one is the easiest accessible vector. We need something that's right in the middle, which will be allowing us to find the direction between them, which is we need to find the perpendicular direction to both vectors, and that will be the cross product. So we would try to calculate the cross product between D1 and D2. The whole idea is we want to find out which direction is perpendicular to both vectors. So then we project P1, P2 onto the vector C, and that projection, the magnitude of that projection would be the distance between the two lines. So that's the whole idea. So the calculation is we want to project the P1, P2 onto the vector C in order to find out projection onto the vector. We had this exercise in I think it was a dot product application. So in 10.3, we went through how to calculate the projection, which is kind of like the parallel to the vector C. So we would have, remember it was U dot V over V dot V multiplied by V. You try to memorize the notation of it. So P1, P2 dot C divided by C dot C multiplied by C. C is like the V in the projection definition we had in 10.3. And then all these calculation, since we need to find the magnitude, property of the dot product have this we really want to find the length. We don't want to find the vector itself. Since the length and magnitude for both, many of the components are canceled. So we have the magnitude of C in the numerator, we have magnitude of Z. Well, two of them in the denominator. So we cancel one of them, which end up being that calculation. So the actual distance calculation is vector P1, P2 dot C divided by the magnitude of C. C is the cross product. So in this sense, the entire distance calculation involves a magnitude, which will absolutely dot product in the numerator, and then magnitude of the cross product in the denominator. So denominator is magnitude of C. The C is actually a cross product calculation. So we need this C is actually a cross product itself. That's a cross product. That's cross product. P1, P2 is connection between the 2-point vector. So figure out a way to make sense of it. I always have to draw everything out until I figure out the formula itself. So if you are like me, not the memory kind, not very good with, I'm not so good with memory, which I always end up being drawing this line, drawing that line, write down the address. Once I finish writing off all of them, start finish figure out how to derive the formula itself. So if you don't want to derive them, you may have to work on trying to remember the relation or remember the formula. We might not be able to finish all example in here, but here is the formula that we talked about. The top one is how do we determine the distance between two parallel lines, or how do we determine the distance from a point to a line? And this formula will serve both. Not a lot of people talking about determining distance between two parallel lines, partly because it's not too hard to do it. But I just want to mention that the formula number one, it will definitely answer that question. The second one is if the line is spilled lines, then we would calculate the distance between the two spilled lines. One thing we should mention that if two lines are skilled, you can imagine this line living in one plane, and this is living in another plane. These two planes are parallel to each other. when you are trying to determine the distance between the skill line, you are actually determining distance between the two planes. Like this one is in this paper, this is inside another paper parallel to it. Distance between the two skill line is distance between the two planes. And we're going to talk about equation of plane in the next section, but this will make sense later. We'll talk about distance between planes. Okay, so these are the formula that we are trying, and then there's a couple of examples showing how we calculate this. The first example, I think we have 28 example distance from point to a line, so I'll do this fast. To find distance from one point to another line, right, you can see equation of line have a point and the direction vector, and that was the point. So we would normally call the first one as point P, and the vector, the direction vector 2, 3, 1 is being called the vector D. So the calculation of this formula will be vector PQ cross vector D, find the magnitude divided by magnitude of D. That's distance between the two. So here the calculation, identify P and Q, therefore we can identify vector PQ, and then the vector D is already in the formula of the line, and then follow the formula. The second one has two lines, and we calculate this one earlier. It's the earlier example that these two lines are skill lines because they don't have intersection and they don't have parallel direction vector. So these are skill lines. So we can work on calculating their distance. So what we're gonna do is we identify point 1, 2, 0 for the first line. Point negative 2, 3, 5 from the second line. Those are the P1, P2. So with P1, P2, you can determine vector P1, P2. And then the D1, D2 is 3, negative 1, 1, 4, 1, 2. So having D1, D2, we can find the cross product of D1, D2. And therefore, coming next will be magnitude of C. Since we have vector C and the magnitude of C in the denominator, we can calculate dot product. So vector P1, P2 dot C, you multiply component by component, add it together, which is 42. So that this is the whole calculation in the book. So you can see the steps is not too long if we know what we're doing. But if we don't remember how to handle this type of question, we'll be drawing a blank. Like, how do we do it exactly? So applying cross product and dot product, this skill line distance calculation involve dot product and cross product calculation. That should be everything that we had in this assignment. I think we had a lot of assignment over distance between two lines. We move forward. See, this is a calculation on are they intersecting, are they parallel, are they identical. Then determine the relation. This one is saying they're intersecting. Let's find the intersecting line, intersecting point. This one is we got two skill lines. The question is what's the distance? So this is the one we might be applying or not applying. This will end our 10.5. I'll see you tomorrow. I'm gonna start talking about 10.6 tomorrow. But if there's any questions you have on 10.5, 10.5 is all our lines. If you're fine with it, we'll start with 10.6. See you tomorrow.
Everybody.